today. Respect programming models, manage Intel Xeon 5s in your clusters for enhanced user experience. Our presenter today is Michael Hebenstreet. Michael is a senior cluster architect at Intel, and he's been a part of the Xeon 5 since the very beginning, and he's been with Intel for about 10 years. So he's been working on the Xeon 5 project for quite a while. If you have any questions throughout the webinar, feel free to post them into the text field. We will get those, and Michael will be addressing as many of those questions as we have time for. And then at the end of the presentation, as you leave the webinar, we have a survey that we would appreciate any of your feedback. So with that, we'll turn the time over to Michael.
Hello and welcome to this presentation. Respect programming models, what does that mean? Well, what I'm trying to give you within the next hour is an idea how we can use Xeon Phi coprocessors without changing the programming models that have been used in clusters for the last 10 to 15 years, essentially since the time our Linux clusters have become available for the first time. I'll start with a little bit of theory, then I will give you a very short demonstration on one of our test clusters, and then I'll show you 3 steps for the administrator that the administrator has to do to create a similar environment. This includes some scripting to start up this type of work within a batch process for the cluster and to integrate within the batch system of your cluster. When we're talking about an Intel Xeon Phi coprocessor, we have to differentiate that very much from a common accelerator. Why? An Intel Xeon Phi system is a computer by its own. It has its processor, it has its memory, it runs an operating system of its own. You can log into this coprocessor and work on this coprocessor like on any Linux system. Couple of definitions that I need to do here to differentiate between when I'm talking about the host, usually a Xeon host, and the Xeon Phi coprocessor. In both cases, we have an operating system. In both cases, we have a Linux kernel. In both cases, we have drivers. So whenever I'm talking about something specific to the coprocessor, I will be calling that the microOS or the microOS kernel or the microOS kernel driver. Now, the Intel MPSS stack, that's the software stack that's necessary to drive an Intel Xeon Phi coprocessor, both includes the host side drivers, the drivers for the OS. It includes the microOS for the Xeon Phi coprocessor, the microOS kernels, the microOS drivers, and a number of utility tools. If we take a closer look at the architecture of the coprocessor running on the about the microOS running on the coprocessor, then we'll see it's very, very similar to the OS that is running on a standard Xeon host. Both Xeon host and Xeon Phi coprocessor are connected on the hardware side via the PCI Express bus. On the software side, we have on the host side a number of drivers that that is all that's needed that the user can start to interface with a Xeon Phi coprocessor, or rather with the operating system running on it. When we're talking about users, when a user gets into a cluster, what they expect is all the machines on the cluster are essentially available on a flat network. And no matter what system they are using, what node in the cluster they are assigned to, they expect to get the same environment. Most importantly, they expect to get the same file systems mounted in the same locations. What we want to do is to treat the Xeon Phi coprocessor as a node inside the cluster. Well, why do we want to do that? That has to do with the programming models that I was starting my talk with. When we start programming on a cluster, the typical programming model is an MPI program. An MPI program will run on the various hosts. The MPI program will communicate either over the Ethernet network or over a fast interconnect like InfiniBand with all the other nodes. And this is a pattern that has been established about 12, 15 years ago. When the accelerators came into the cluster, you had to change your data structures, you had to change your program. You have to examine which part of the code is worth offloading to the accelerator, or the same model you can do on the Xeon Phi coprocessor is offloaded to the mic card. But that means changing your code. And it is something users are very, very unhappy to do. It would be so far better if the user could simply run an MPI process on the coprocessor and treat the coprocessor as any other node in the cluster. That means the program itself remains largely intact. You do not need to change the programming structure. You do not. You can rely on everything staying the same. This is especially true if both on the host and on the coprocessor you have a similar set of tools and libraries, like the Intel compiler for C and Fortran, combined with the Intel MKL mass kernel library. Especially important, this will if we get on to the next stage of the Intel Xeon Phi processor, codenamed Knight's Landing. This processor is targeted to come out this year, and it will also be available not only as a PCIe coprocessor like the current version, but it is also available as a standalone CPU and therefore integrate into a cluster far more seamlessly than any type of accelerator can do. That also means that if you do not want to run code on the host because the hosts essentially become useless compared to the compute power of the Xeon Phi coprocessor, you should be able to run your MPI processes strictly on the coprocessors. That the hosts are then used for transporting the data and connecting the coprocessors via Ethernet or via InfiniBand is to the user completely unimportant. The user is and that are the people who spend most of the time developing and optimizing the code. They should their work should be made as easy as possible. And if you do not need to change your data structure, you win. Our own test cluster that we are using in HPC for benchmarking is called Endeavor, and has as its core 360 nodes with current technology, each of those nodes equipped with 2 Xeon Phi cards. We also have about 100 nodes, both of previous generation CPUs and next generation CPUs for testing available, but it is here of second importance. One point that every user on our cluster has, we have a number of different file systems that are used for special purposes. So there is the home storage system, which is based on NFS, but we also have Penesis and Lustre systems in the mix. These systems now all should be able to be mounted directly on the Xeon Phi coprocessor, because the data are located inside the cluster at these locations. So we need to have support on the Xeon Phi coprocessor for these file system types. Luckily, NFS is supported out of the box. Lustre is supported directly by Intel via the Intel Enterprise Lustre Edition. Panasys also offers a native Xeon Phi client for everyone interested. And that means our users on Endeavour can have all the file systems that they have available on a normal Xeon host available on the Xeon Phi system as well. They also have a number of tools available that are run natively on the Xeon Phi to be as close as possible to what is available on the Xeon host. What does that mean for a user? Let me give you a quick demonstration on that part. So I'm here on my test cluster. I have the file system, my home file system available with a number of files. If I connect via SSH to the Xeon Phi card available on the system, I see the same file system. No difference here. For MPI, Intel supplies the Intel MPI library with special Xeon Phi support. And the combination of the Intel C compiler, the Intel MPI library, and the common system image that I have here between my Xeon Phi coprocessor and the Xeon host makes it possible to compile and run a program extremely easily without doing any changes on the system. Let's start with a very simple MPI program that does not nothing more than doing a little bit of communication and printing out the node name where the MPI process is running. First thing to do for me is to set up the environment for MPI and for the Intel C compiler, so that I now have the ICC compiler and the MPI compiler in the path. Then I set two environment variables. Intel MPI mic equals enable simply tells the system enable the support for Xeon Phi support. A second environment variable creates a postfix. What a postfix does will become clear in a moment. I also have set up a host file. The host file contains here two Xeon Phi cards. You notice the extension dash mic and two Xeon hosts. Now compiling my test program first for the Xeon host architecture. Very standard, I create an output file MPI test. I do the same thing to create a binary that runs natively on the Xeon Phi. This is done by adding the option mmmic. I also give it a name that is the same name as the original binary, extended by the IMPIMIC postfix. So the complete name now is mpitest.mic. Nothing more is done. I do not change my program in any way. I just compile it twice to get two binaries that run on the two different architectures. Then I start my MPI run. An option to run the MPI via SSH. I want to run one binary or one MPI process per host. I give it the host file as parameter that we had earlier. I tell it to run 4 MPI processes in general, so that on each of my 4 hosts, one MPI process is started. I tell it to start everything up over the Ethernet network, and the program I'm running here is the MPI test. Notice that I did not say anything about MPI test mic. That was added automatically by the Intel MPI library. And now my program has been started 4 times in the 4 processes, and 2 of those processes were running on Xeon Phi hosts. How is support for the interconnect? This first one was run over, this first example was run over Ethernet. Now let me give you an example by running an, by running a program that gives us some speed information. In that case, it's the latency between 2 different nodes. Again, I compile one program for the Xeon host. I compile it a second time with the MMIC option and the different host name. And now I run this program once, again over Ethernet. In that case, I gain latencies in the range of 300 to 350 microseconds. Now let's do the same thing and run it over InfiniBand. The only thing I change here is the IMPI device parameter. In this case, the parameter is for RDMA, remote direct memory access, with a specific InfiniBand interface. That's the Mellanox IB code. And immediately the same program runs, but this time with a latency that is about a factor 30 better than before. But again, the same program without any changes was run immediately on Xeon Phi hosts and Xeon hosts at the same time. That means it becomes for the user very, very easy to run, to compile and run an MPI program out of the box. Now there's a caveat that I need to point out. We did not optimize the program yet for the Xeon Phi architecture. The Xeon Phi processor has 60 cores. Each core is has symmetric multi-threading for 4 threads, so the Xeon Phi coprocessor should be treated as a system with 240 or more CPUs. Compare that to the 30 CPUs that you have on a 30 cores that you have on a standard Xeon host. The thing that Intel helps you here with, between both the Xeon host architecture and the Xeon Phi architecture, we have a common set of instructions. We have a very, very similar architecture. We have a common set of tools. So compiler, VTune amplifier to detect bottlenecks, libraries are on both platforms the same. All this means very often when you're trying to optimize a program to run on a Xeon Phi system, and then you take back the same program, just recompile it for the Xeon host, and you most often you will notice the Xeon host code will also run better. That is the benefit of having 2 architectures that are so closely related to each other. Combine that with the option to keep the basic MPI structure completely in place, and your users will experience a far easier way to make use of the new architecture. Where is the price that you have to pay? The price comes for the system administrator. For the system administrator needs to do a bit more work than they might need with a standard accelerator, or if you use the Xeon Phi coprocessor in offload mode only. And but as every cluster is different, it becomes a little bit of a problem to give you a list to step through one point by point, because on some clusters some of these points will not work out. So I can only give you some general guidelines here, what it needs to be done. Naturally, first of all, you need to install the host side of the system, and you need to install the host side drivers. Very often it's here necessary to recompile parts of the MPSS stack, specifically the Linux kernel drivers. But as MPSS is available in source for almost all the tools provided, this is something done very easily. Once that is done, we can get the card running with a couple of commands. We load the driver, we start our MPSS daemons, we do a basic configuration. That should be all that's necessary to get the card booted into a basic state. And in my experience with end-user customers, they very often do not know that in this configuration already you can access the card via the Minicom program to see if the card at least is running, even if there is no network or no InfiniBand yet supported. Speaking of InfiniBand support, what can we offer here you? We support both Mellanox, ConnectX, and Intel TrueScale systems. There are a various number of driver packages that support these cards that are also supported in concert with the MPSS stack. But for almost all of them, very often you will need to recompile parts of the packages because your kernel is very different from a standard installation. Once that is done, second step, again, only for the administrator, we need to configure our Ethernet and we need to configure our InfiniBand support. What is necessary on the Ethernet side? The easiest way to do all that is to configure the cluster, and that means both the Xeon hosts and the Xeon Phi coprocessor in a flat cluster model, so that a user can do a ping or an SSH to each node that includes the Xeon Phi cards, as well as the Xeon hosts. And Linux provides a nice feature for that. That is the bridging interface. We can combine both an interface for the host and the Ethernet interface on the Xeon Phi processor into one physical interface that's located on the host. If we then give both the Xeon Phi card and the Xeon host an IP address that is valid inside the cluster, all that is needed is completed. Here, example how to set it up. It's on Red Hat very simple. You need to edit a couple of files. You need to create one bridge file that on the host that contains essentially all the information for the Ethernet side on the host. And then the two interfaces, the ETH0 interface on the host side and the mic0 interface, will be hooking into this bridge. They don't get IP addresses by themselves on their host side. They only get you only need an IP address on the Xeon Phi coprocessor side. Again, this is one file. Standard location for the host site is in var MPSS mic 0 etc network interfaces. Here at that point, you set the IP address and the network mask for the coprocessor. The InfiniBand support, there is only one item that you need to take care of. We very often the Xeon Phi card will be reset in the daily cluster life. When you do that, after you have reset and booted the card with a miccontrol -R and miccontrol -B command, then you need to restart the services ofet-mic and mpx-yd. The first one, ofet-mic, is to get the basic support for InfiniBand running on the Xeon Phi coprocessor. The mpx-yd daemon is to optimize this connection speed. So with only ofet-mic started, you will get a working system, but optimum performance via InfiniBand you only get with the service daemon started. With that part done, the final step is the real cluster integration. And to get the common system image that I've been talking about earlier, on the Xeon Phi coprocessor we need two items. We need to mount all the file systems. If you have if you have only NFS, this part can be done in the same way you do an NFS mount on the host with two caveats. Be careful with locking and be careful about NFS versions. The Xeon Phi coprocessor by default is set to NFS version 3. The second item, we need to inform the Xeon Phi coprocessor about the user allowed to access the system. I've been asked a couple of times what in previous webinars what type of directory systems are supported on the Xeon Phi coprocessor. Is NIS supported? Is LDAP supported? Can I use Kerberos? Well, we have support for these items, but in reality, in most of the cases in a cluster, you will not need that. You have the support already running on the Xeon host, and all the information that is needed on the Xeon Phi coprocessor is actually only the user ID and the username. If you add both of these information to the password file on the Xeon coprocessor, you're good, and you don't need to run any extra processes on the Xeon Phi card. It's not really advisable anyway to have multiple users being allowed access to one Xeon Phi coprocessor at the same time, because that is a system that has very limited amount of memory, only 8 to 16 gigabyte, compared to a Xeon host that might have up to 256 or more gigabyte of memory. It also does not have a local file system that is provided by disk, or the local file system /TMP is provided by RAM disk. All these limitations, and you have the same limitations on the common accelerator as well, mean there should only be one user at a time, and that means if you follow these guidelines, you only need one additional line in the password shadow and group file to make everything available for the user. On the host side, the ID command will give you all that's needed, and then with 3 lines of shellcode, you get immediate support for whatever you need on the Xeon Phi coprocessor. No matter if there's running a Kerberos, a NIS, or an LDAP system on the host. If you put everything together, okay, I have here a question from Chris Stackpool on the I want to answer that right away. Question about user management. I have a few hundred users. I don't want to manage all those users by hand. Having it controlled by LDAP or something that would mean I don't have to manage the user. How do I automatically manage the user? That comes exactly with the startup script. We have an cluster. I can assume your cluster is running a batch management. During when a job starts up, usually you execute a prologue script, and if the job exits, you start an epilogue script. These are the right places to put in a startup of the Xeon Phi host. Here an example what would happen. This script takes one item as a parameter, and that parameter is the username. I first do a reset of the Xeon Phi coprocessor, then I do a boot of the Xeon Phi coprocessor. Once the system is up, I copy over the host file to be up to date, and then I add those three lines to etc passwd, to etc shadow, to etc group on the Xeon Phi coprocessor that are necessary for this specific user running the job. So that can be done completely automatic. At the end of the script, I mount my file systems, and finally I also start the Koi daemon as a user for security reasons, so that I have no issues with a Koi daemon that is used during offload processes accessing any other files. As I said, this is something you can put in your cluster prologue, and that way you don't need to do anything more to manage the user on the Xeon Phi coprocessor. I hope that answered the one question you had here. Second question coming in, let me go back, sorry. To this. Second question coming in, what is the MPXYD daemon? The MPXYD daemon tries to optimize the InfiniBand packet flow. Depending on where your processes on the hosts are running, where your InfiniBand card in the system is located, where your Xeon Phi card in the system is located, the the flows of the data packets should go over different cores, different PCI buses, and so on. The MPXYD daemon tries to optimize that and tries to give you an nearly 100% efficient InfiniBand packet flow. So Paul, I hope that answered your question. With that being said, let me give you an example what we are doing on Endeavor in our prologue. The first thing is we set up as I outlined the Xeon Phi coprocessor. We ensure that the user that is running the job can do a passwordless SSH to the Xeon Phi coprocessor. We mount all our file systems. We also do a number of security checks to ensure that our cluster, who has a very high security standard, does not get into any problem because of the Xeon Phi coprocessor. So we remove, for instance, the inetd. As I outlined before, we restart the Koi daemon. We also set up the SSH environment on the Xeon Phi coprocessor with user-defined limits, for instance, the stack limit, the max mem locked limit, and so on. There's another question coming in: why is it necessary to kill the COI daemon? It is not strictly necessary to kill the COI daemon. The COI daemon runs on the card normally with a preset user ID of the user mic user. This in a cluster, I personally, as an administrator, do not want such a common setup. What I want is that a process like that might access other files is automatically running with the ID of the user running this specific job. So that no way what the user is doing, the user cannot break out of the environment and cannot access any other type of files that they should not be able to access. Normally, it is not a very big deal, but I prefer, as I already said once, I prefer to run a very secure and very strict environment. And every code that is developed, sooner or later you will discover errors there. Unfortunately, it's also true for the COI daemon. We had a number of issues where the COI daemon opens up security holes. All of these issues are fixed by now in the latest MPSS distribution, but I cannot say what the future will bring. And in a cluster where I have people from different companies with, for instance, HP and IBM sometimes running at the same time, and I really want to make sure they cannot break out of the various sandboxes. That's why wherever possible, I increase the security beyond the standard limits. And one of those is, what are the methods I'm using here is to restart the COI daemon that it's run as a normal user, specifically as the user owning a job. That way it cannot happen that they access any other files, but the files they really have access to. Pedro, I hope that answered your question. We have a number of resources available. There is a Xeon Phi coprocessor developer site. There is a community forum, but what I don't have here in that, for administrators, we recently brought out a very new Intel MPSS user guide that is a couple of 100 pages, contains knowledge for administrators that is available at the same site where you download the driver software. And with that, I hope I gave you a little bit of information, hopefully something new and things you can use. And with that, I'm up for your questions. Thank you very much for listening.
Yeah, great. Thank you, Michael. Yeah, we do have some more time. Appreciate the questions that have come in so far, and we do have time for more. If anyone would like to send in a few other questions, again, we remind you that we have a survey that we would like to have you fill out for us as you close the webinar window. Your feedback is important, and we appreciate any of the feedback that you have on this webinar, as well as any ideas for future webinars. We've had several questions on a copy of the slides. Yes, Michael's slides will be available probably within about a week or so. We will post those along with the recording of this webinar so that you'll be able to view it again, as well as have the slides for your reference. I know we got several notes on people trying to take quick notes, but you will get this slides in the webinar. Let's see, there's questions, a few questions coming in here. One asks, what are the cases where we wouldn't want bridged mode?
I
Why
have
bridge
one.
versus not bridge? Yeah.
I have one customer who does not want bridges. I don't really understand why he doesn't want it. He will have his reasons. If you are not using bridging, you want to run Xeon PHYs in a cluster, then you will need to use a lot of routing, and you will create very large routing tables. It is possible to do, but my advice is strictly against such a setup. My advice in a cluster, so whenever you have more than one Xeon PHY system available, then please switch to a bridged networking. Everything else will create a lot more work for you. On a single node where you don't have this type of problems, the default routed approach is valid. But in a cluster, I have to really, really disapprove of such methods.
We had one request. If you could go back to the reference page.
Done.
Yeah, perfect. And then
We have a question from Craig Rees. What is the function of the koi daemon? I need to go back here to the programming models. The koi daemon is used during offload. What happens during offload technically? Inside your program, when you compile it, you create for all the functions that are offloaded, essentially a piece of code. During the initialization of your program, these pieces of code are transferred to the Xeon PHY coprocessor, and the process doing this transfer on the Xeon PHY side is the koi daemon. The koi daemon is also responsible that during the runtime of the program, when you exchange data with the Xeon PHY coprocessor, doesn't matter in which direction, this data transfer will be done by the koi daemon. So the koi daemon is a program running on the Xeon PHY that is a necessary part of the offloads infrastructure. But because it's a program and because you execute normal code on the Xeon PHY code, it's a if you during an offload operation, you log into the Xeon PHY code and use a standard Linux tool like an strace or a ptrace command, you will see there is a normal program running. Same type of infrastructure that you have on the Linux on the Xeon host side. So then let's go back to this side. We had that bridged. Next question, we face the problem while trying to run linpack nodes which are having PHY and which are not having PHY, but it gives me a lot of IB errors. However, it ran but very poor performance. If you run Xeon, if you run a system where you have nodes with different capabilities, you need to be very, very careful how to set up your data structure. If you don't set up the linpack data structure correctly, and you have then the startup node will assume it has the same type of nodes on all the other processes running in the job, and that can easily lead to a single node slowing down everything. Next question. is any improvement for programs with high degree of AVX2 optimizations from Fernandez. I do not really understand the question. Can you please explain that a little bit more in detail what your problem is here? Okay, the TMI library. Yeah, mic is on mute. The TMI library, you can no, sorry, let me first repeat the question. The problems on the Lindbeck systems is because they experienced differences in the RPMs that were installed, and the TMI library got removed during the installation. The TMI library is also available in Intel MPI by now. So one approach would be to point the TMI config to the TMI library supplied with Intel MPI, so that you don't need to install the TMI library on all the nodes. If not, then you also can simply copy out the TMI library from any of the RPMs where you installed them and use them this library on the nodes where the overhead stack was changed. But I again point here also to the new MPSS user guide. This MPSS user guide has a number of chapters how to improve the installation of MPSS with Intel TrueScale cards or former QLogic TrueScale cards. Xeon 5 should work with AVX2, yes. The question was if Xeon 5 works with AVX2. Yes, I think that is the case. Next question is, what is the best way to compare the performance of Xeon Phi that we are measuring to the, in our application to what is technically possible? In that case, I have to point out to a book that recently came out. There are two books by James Reinders and Jim Jeffers. Intel Xeon Phi coprocessor high performance programming gives you a very good introduction in what should you do when programming for Intel Xeon Phi coprocessors. And new that one has already been out for over 1.5 years. Then there's a book, High Performance Parallelism Pearls. This book contains about how many? 28 special cases how to people optimize for specific problems on Xeon Phi. Michael, can you please make sure that these that the names for those two books are distributed to our audience?
Sure.
And the first one, Intel Xeon Phi coprocessor high performance programming, specifically takes you to through an example what is possible on a Xeon Phi and how to reach it. Ram Mohan, one more thing, if you maybe you can come back to me after the meeting. I can give you my email address and we can talk about your configuration problem a little bit in more detail.
All right. We still have a few more minutes if anyone else has a question.
And I have one thing to apologize for. I'm Austrian. I'm sorry for my German accent.
There's another question that just came in, Michael, about is Xeon Phi effective for parallel problems?
As far as I know, yes, it is specifically effective for embarrassingly parallel problems. But again, I have to refer to the books that I spoke up, or we have to connect you to one of our expert in Xeon Phi programming. I'm a cluster architect. My specialty area is how to get Xeon Phis running in a cluster. I'm not a specific expert on Xeon Phi code optimization. So I couldn't give you any direct example here. But with the books and if necessary, I'm pretty sure that James Reinders is happy to help with any specific question on such problems.
All right. Well, it looks like we've come to the end. Again, thank you everyone for your participation and your questions. Thank you, Michael, for the presentation. Again, if there's any questions, any other, you see the resources there that you can always go to, and the slides, all these will be ready for you in about a week or so. We'll let you know when they are available. So again, thank you everyone for joining us, and hope to see you at another webinar very soon. Thank you, everyone.